right. Last day. You guys ready for the finals? No? Ready for them to be over? Yeah. All right. So today, plan is to go over this last homework, the solutions, and any questions you guys have if you'd like me to cover any particular topics. At this point, your formula sheet should have been posted at least a week ago. I think I made sure it was current. So if there are any issues there, let me know. I think it should be the current one though. The exam, I think I mentioned last time, it'll technically be about 50% this sort of stuff, so what we've been doing this last unit since the previous exam, and 50% stuff before that, so partly cumulative. And part of that's just because most of the topics are relevant for all of the stuff, right? Wastewater treatment, we also use disinfection, right? We also use sedimentation. Sometimes you use membrane systems. So it all kind of comes together, and I just want to give a little bit of an overview on it all. So you can expect it to be maybe just a little bit longer than the other exams that we had. I think exam 1 was a little longer. Exam 2 was a little slightly shorter, but that had that issue on that first question. So assuming no issues, then it should be manageable within the 2 hours. You can expect basically, I think, what you saw from the other exams. So if they are long and involved questions, maybe 4 of them. If I chop it into shorter questions, maybe 5 or 6, but same length target there for the 2 hours that you'll have. Trying to think. The exam date should be correct in the syllabus, and I'll double check with you here real quick. I think it's Wednesday, if I recall correctly. I've not made the exam yet. That's not obvious yet. Yeah, Wednesday, December 7th at 10 a.m. I'm going to turn off these front lights here for you. Okay, so I think that should be correct. Any doubts, you can always check the LSU website. All right, so with that, any questions you'd like me to answer? Any topics you'd like to have some review on or anything? Okay, if not, I'll just jump straight into the homework solutions, and then you can get about your studying and everything. Okay, so problem 1, we have a wastewater treatment plant using activated sludge system. For primary treatment, 3.5 cubic meters per second of primary effluent. So what we're talking about there is we have some primary treatment, which usually is like the bar rack, sedimentation chamber, kind of the first steps. Then we take that into our secondary treatment, which we consider the aerated tank, waste activated sludge. Usually this sludge just kind of goes to waste or to possibly, yeah. We're just not going to talk about that. It's not relevant. Okay, so this is our typical system. That means the primary effluent is this stuff coming in here, right? So this is the primary treatment, this is the primary effluent, and that's going to be kind of what we're talking about. So from here, we're given, so Q is 0.35 cubic meters per second. The mixed liquor, that's referring to X inside here, that's 2,500 milligrams VSS per liter. We're also given the RAS, so the return activated sludge concentration. So XR is 10,000 milligrams per liter. We're also given the substrate concentration of the primary effluent, that would be S influent, that's the 220 milligrams per liter. We're given an F to M ratio and a cell retention time. So theta C, 9 days, F/M, 0.52 milligrams BOD per VSS per day. Okay, so with all that, part A is asking what is the volume in this tank. And if we take a look, we have in our F to M equation a pretty handy way to calculate that. So it's our equation for the food to mass ratio. Essentially, it's how much food is in this tank, right? So the volume of it will matter. This is the Q times that incoming substrate divided by the volume times X. So we can just simply rearrange and say the volume is equal to Q S naught divided by F/M. Now remember, this is just one variable here. We're not multiplying by M, dividing by F, any of that. We're just keeping it F/M right there. So then with that, we can put in our terms. So 0.35 cubic meters per second times that 220 milligrams per liter BOD divided by that 0.52 milligrams BOD per VSS per day. And here on the bottom, we also have, or excuse me, we have, that's in days, so we need to convert that to seconds, or this one to days. But we also have that X concentration we were given, 2,500 milligrams VSS per liter. Okay, so looking at the units, we still need to convert to get like terms for the time. So I'm going to go ahead and multiply the top here by how many seconds in a day? 86,400 seconds per day. That'll get us per day units there. Once we put all that in, our volume should come out to 5118 cubic meters. All right. So pretty simple to start with. Part B says, what is the waste-activated sludge flow rate? So again, just going to draw this up real quick. So what we're looking for is the QW here. That's the question, the flow rate for the waste-activated sludge part. So we're wanting to solve for that. We are given a lot of the other things. We have an equation, theta C, if we were to take a look at our equation sheet, that has some information here. So theta C, we know is 9 days, but the equation we're given is Vx divided by QW XW. So we have basically everything there. We can say QW is going to be Vx divided by theta C times XW. Now we don't have directly XW, but we were given XR at 10,000 milligrams VSS per liter. And that should be the same exact thing as the XW, right? So if we have some amount of bacteria concentrated here, it flows down, it splits into two directions. There's nothing that's going to change the concentration by sending it through two different pipes. So with that, then we can put in the numbers here, and QW, so let's go ahead and just write that out explicitly here. So XW equals XR. So QW then would be 142.2 cubic meters per day. Since the next question is going to ask us, to deal with flow rates again, I'm going to go ahead and convert that to seconds and say that's also 0.00165 cubic meters per second. All right. So again, I think the major complication for any of these types of problems is probably going to just be understanding the variables, where they go, what they mean from the wording. Okay, so last, or not last, but part C, we say we have what is the flow rate for the secondary treated effluent. So what we're talking about is the effluent here going out of that reactor. It's not going into a landfill. That's what we would be discharging. So QE is the question. And we know that essentially if Q is coming inside here, we have some Q recycle here. We have QW and QE. Well, Q has to be, since the recycle is kind of internal, Q is going to be QE plus QW. So that means QE is simply going to be Q minus QW, which will be 0.35 cubic meters per second minus this 0.00165 cubic meters per second. So QE then will be 0.348 cubic meters per second. That's kind of what we'd expect. Most of the wastewater is leaving as wastewater that's been treated, not as this sludge stuff. All right, so part D says what is the hydraulic residence time for the activated sludge, and we remember that when we're talking about, in this case, it's V over Q. It's definitely not the same thing as theta C, right? It's two different things here. The one's the solids, or the cells, the bacteria cells. So when we consider our system, and there's possible confusion here with the fact that we have recycle, right? So if we have Q and QR going into our tank, you might think to yourself, well, why is this Q, why are we using Q, not Q plus QR? Because the answer here should be that 5118 cubic meters divided by our 0.35 cubic meters per second. We can convert that to days if we like. 1 day per 86,400 seconds. This theta is going to be 0.169 days. And the reason we don't have Q plus QR is because we said that essentially all of the volume where we have a reaction happening is here. This volume in terms of reactions is 0 here. So we don't have any important volume there. And so really, if we draw a mass balance like this, or a control volume rather, then the only space with reactor stuff happening is in that reactor, and the only flow going through it is Q. So it's this V over this Q within that control boundary. Now, another way to think about it is that this QR, yes, it's adding flow that's going through the system, but that amount of flow is also coming back around again. So that amount of flow, that same amount of flow that gets added every time, sees it again every time, right? So it kind of equals out that way. So that's just a little explanation why we're using Q, not the addition of Q and QR. All right, any questions, issues there? Okay, so problem 2, we have incoming wastewater with a BOD 5 equal to 200 milligrams per liter. It's treated in a well-run secondary treatment plant that removes 90% of the BOD. So we have some sort of treatment here that's going to take away 90%. What's coming in is 200 milligrams per liter of BOD. So that means what's going out is going to be 10% of that, so 20 milligrams BOD per liter. And this could be the confusion right here. So this is the treatment that's described. 90% of BOD removed. And so we are tasked to run a 5-day BOD test with a standard 300 milliliter bottle using a mixture of the treated sewage and dilution water. We don't need any seed, so we're not dealing with that complication. And we're going to assume the initial dissolved oxygen is 9.2. So roughly what maximum volume of treated, again, that's telling us something important here about what number to use. Wastewater should be put in the bottle if we have to have at least 2 milligrams per liter of DO at the end of the test when we fill it all the way. So what we're after is the volume of wastewater in the bottle, and we can get that essentially from the fact that our dilution factor, once we find that, is related to the volume of the wastewater divided by the total volume, which we know is 300 milliliters. So we don't know the P, but that is an equation that can get us that volume of the wastewater. So where can we find P? Well, this 5-day BOD test, we know that's going to be DO initial minus DO final divided by P. So since we should know each of those factors here, we can say P is going to be equal to that DO initial was 9.2. The DO final had to be at least 2, so that's going to be 2 here. So that's our maximum waste scenario. And divide that by the BOD5, which is going to be the BOD5 of the treated wastewater, which was given in the form of this process. So that's going to be our BOD5 for this case. Okay, of course, these are milligrams per liter as well. Okay, so that means we have essentially 7.2 divided by 20. That comes out to be 0.36 for our value of P. And that means that the volume of the wastewater is going to be essentially 0.36 times 300 milliliters. So our answer then is 108.0 milliliters of wastewater in that bottle. Now, had you calculated it based on the 200 milligrams per liter BOD, so the untreated wastewater, then you would have had 10.8 milligrams per liter, or excuse me, 10.8 milliliters here. It has been off by that factor since you didn't factor in the treatment and where in the process we're looking at. Okay, yeah.
So when you use when that is used to 200 milligrams times the 1 minus 9%.
Yeah. Yeah, so I just said if it's removing 90%, I'm going to take 10% of, so 10% is remaining.
Oh.
Yeah. So that's exactly what I did. I just kind of did it in my head. I probably should have been. So 1 minus the 0.9 will be the percent remaining, because the 0.9 is the percent removed, right? Is the fraction removed. So it's removing 90%. That means 1 minus that is the amount remaining. That means we have 20 milligrams per liter BOD remaining after treatment. Okay, so then part B says if you make a mixture, half water, half treated wastewater, what DO do you expect after 5 days? And so we just saw that 108 milliliters was the maximum we could add to have 2 milligrams per liter of DO remaining. So we know it's going to be less than 2, obviously. So we can check our answer like that. It might reach 0. If we get a negative number, we just have to say 0 because it's not we can't have negative amounts of oxygen. So when we do the test here, then we still have the same BOD. That's going to be the 20 milligrams per liter. We have the same DO initial, which is 9.2 milligrams per liter, minus what we're trying to find. And this time we had a dilution of 1/2, right? So this will be 0.5. So we can take 0.5, multiply that by both sides, and say 9.2 minus the DO final is equal to 10. And we see we can add DO final to both sides, subtract 10 from both sides, and see the DO final is a negative number, negative 0.8. So that means our measurement is actually 0. Okay. So if it had more oxygen in it, or if we had maybe unsealed it, let some more oxygen in, then it could have consumed a full 10 milligrams per liter of oxygen. But in this case, just 0. All right, so problem 3, we have a BOD test, another one. This one's run using 10 milliliters of treated wastewater mixed with 200 milliliters of pure water. The initial dissolved oxygen of the mix is 9.0 milligrams per liter. After 5 days, the DO is 3 milligrams per liter. After a long period of time, the DO reaches 2 milligrams per liter, and it no longer seems to be dropping. We're assuming no nitrification effects here, so everything is carbonaceous. So part A says, what is the 5-day BOD of the wastewater? Okay, this is going to be simply exactly what we were doing a moment ago. The DO initial 9 minus the DO final after 5 days was 3. Divide that by our dilution factor. And here we had 100 milliliters of this sample and 200 milliliters, so a total of 300 milliliters of volume total. And so that gives us a P of 1/3. Okay, so in this case, this becomes pretty simple. 9 minus 3 is 6. Divided by 1/3 is multiplying by 3, so that becomes 18 milligrams per liter of BOD. Okay. So part B then says, assuming no nitrification stuff, estimate the ultimate carbonaceous BOD. So what we're talking about is L naught here, or we could perhaps describe it as BOD at some infinite time, right? The most amount that could ultimately be consumed if we give the bacteria as much time as they want. And we were told that after a long period of time, it reached 2. So what we can do is we can say, well, this is kind of the same problem. We just reached 2 instead of 3. And so that means we've got 7 now on the top times 3 by dividing by 1/3. And so that gives us 21 milligrams per liter of BOD. All right, makes sense? So this could be a spot where you might look at the formula sheet and think to yourself, oh shoot, I need more, like a fancier equation here. So just recommend that you take care to look, find the most direct route if it's there. Okay, and I'll pull up the formulas here. We'll use this in a moment anyway. All right. So we're going to use essentially this. We'll use this in a minute, this BOD at time t. You didn't need that for this part of the problem. This is kind of what I'm commenting on. So part C says what would be the BOD remaining after 5 days has elapsed. So BOD remaining, that's LT. That's going to be the ultimate BOD, or BOD at an infinite amount of time, minus BOD at some time t. So the BOD infinite here, we could rewrite that as L naught, which means essentially we've got some amount that has been consumed in the 5 days or in the 3 days or however much time we give it. And we're comparing that to how much was there, like the ultimate amount to begin with. So really this is just LT is that ultimate, which we calculated 21 milligrams per liter minus the 18 milligrams per liter that were consumed in 5 days. So L at 5, let's say, is going to be 3 milligrams per liter.
I have a question.
Yeah.
So the formula sheet has formula for BODW and BODT. What is the difference between the two?
Okay, so let me pull that up. Okay, so this BODW, we're typically talking about a 5-day test, but the W there is kind of in reference to, we're looking at the BOD in whatever wastewater sample we're measuring compared to the BOD that was in the seed water versus the mixture of seed water and, or dilution water and the waste sample. So that's kind of to help us keep the mixture separate from the dilution water in that more elaborate thing. But usually that'll be like for a 5-day test. So you could probably add a subscript 5 if you want to there. Because you technically, you certainly could do a 10-day BOD test and use that same formula for that. It's a good question. All right, so we've got 3 milligrams per liter there for that. Now, part D then is going to use that other equation that I was just highlighting that says BOD at some time t, we can predict based on these kinetics. So it's BODT equals L naught times 1 minus e to the negative kt. This k being a rate constant of BOD removal. And so this part D is asking for that k in particular, estimate the reaction rate constant k in per day units. And so essentially, we have calculated each one of these now. And so we can set this up and solve it. I'm going to go ahead and rearrange for k. So we can just work on getting this k term by itself. I'll say BOD t divided by L naught is equal to 1 minus e to the negative kt. You can rearrange those and say e to the minus kt is equal to 1 minus BOD t divided by L naught. From there, we can take the natural log of both sides and say that negative kt is going to be equal to the natural log of 1 minus the BOD t divided by L naught. And we could divide by negative time, which is going to be 5 days, say k is equal to that stuff. That stuff divided by time. Okay, so when we put all that in, our k should come out to be 0.389 days to the minus 1. That time there on the denominator is will give us the per day. The natural log of some quantity is often unitless, or should be unitless, so that works out. Okay, and by the way, I should probably have filled this in. So this will be negative natural log of 1 minus BOD at time t. That was our 18 milligrams per liter divided by the 21 milligrams per liter. All that divided by 5 days. Okay, now we could use a different day if we had some information. If we did a 3-day BOD test, it would work just fine. We just have to use the 3 days there. All right. So last question we have, suppose the only source of BOD in a river is untreated wastes that are being discharged from a food processing plant. The resulting oxygen sag curve has a minimum value of DO somewhere downstream equal to 3 milligrams per liter. Just below the discharge point, the DO of the stream is equal to the saturation value of 10 milligrams per liter. So the first part says, by what percent should the BOD of the wastes be reduced to assure a healthy stream of it with at least 5 milligrams per liter of DO everywhere? What would be the primary, would a primary treatment plant be sufficient to achieve this reduction? Okay, so right now we've got it with the oxygen sag curve with a DO there, and we need some curve that's going to, well, starting at the same place, going to reach a higher value of dissolved oxygen, so a smaller deficit, something like that, where the minimum there would be 5. Okay, so that's the target here, and let's just write a couple things out that we may care about. So the initial deficit is 0 because we start at saturation. Okay, that turns out that that's going to be pretty important. If we take a look again at our equations here, I can expand that a little bit. If we take a look, we have several equations for this type of analysis, right? All those ones we didn't integrate in class. We have this deficit term here in this equation. So that portion will go to 0 when we do any calculations here. Also, for the time at which the critical point happens, has the deficit over here, the initial deficit. So that whole term goes to 0. And before we even begin, we can take a look and say, okay, well, this is hopefully going to simplify a few things. And one of the things is, well, if we change the amount of deficit, does that, or the amount of DO at the minimum, does that mean the time will change? Because that could complicate things. And this time equation depends on the initial amount of waste, but that's in the same term as it depends on the initial amount of deficit. So if that whole thing goes to 0, then it really just depends on the KR and KD. Those are going to stay constant for this river. So the timing of the critical point is not going to change, which is quite handy. So then we look at the critical point equation, or excuse me, the deficit equation, and we have this guy, and we take a look, and essentially what we want to know is if we change the D, that deficit from 7 milligrams per liter missing oxygen to 5, what kind of change do we have to have for L naught? Well, if you look here, and I'll write it up in just a second, it's directly proportional, right? It's a 1-to-1. If you change one of them, the other has to change, because the KR, the KD, the E to the minus K and T, all of that is all constant. And so, and we don't have this extra factor in there. So it's quite convenient that we have a starting deficit of 0, because when we want to, essentially, we know that we have some L initial for the bad case, and we need some reduction so that we can achieve some L initial for the 5 deficit case. And that's kind of the question, is how much reduced do we need? for going from d equals 5, or from d equals 7 to d equals 5, right? Say to a target there. So when we take a look at this equation for deficit, that's our equation here. I'll write it up. We have KD times L naught divided by KR minus KD times e to the minus k dt minus e to the negative kr t. All of that plus this d naught term that's going to 0 times e to the minus krt. Okay, so that means that for any change in d, or any change in L naught, is essentially going to be the same change in d, right? They're directly proportional because they're in the equation there. Everything else is constant. Okay, so that means when we want to compare the difference here, so the deficit that's bad, we'll say, or let's see, how should I say this? The target deficit divided by the bad scenario, the current, is 5 over 7. So that's going to be the L naught target divided by the L naught bad or current, right? So that's the ratio between the two. So the target is 5/7 of the current situation. And so if we take this as a fraction, that's 0.714. So we can say the target is 0.714 of the initial. That means we reduce it. We need it to be reduced by 1 minus that. So that gives us a reduction of 28.6%. Okay, so it turns out we didn't need too much of the crazy equations for this point, but we did have to take a look at them and see that we have some simplifications. Okay, part B says if the stream flows 60 miles per day, has a reaction coefficient Kr equal to 0.8 per day, deoxygenation coefficient Kd 0.2 per day, like it was shown in the figure. How far downstream in miles would the lowest DO occur? So here we're using that TC equation to find the critical TC, and of course we're going to get X at that critical time by saying that's going to be U times time critical, and then that'll be our that'll give us our distance. Okay, so TC, we have the equation. This is 1 over Kr minus Kd, and we notice that Kr is not equal to Kd, so we're fine to use these equations. Multiply this by the natural log of Kr over Kd times 1 minus, and then we have this d naught times some other stuff, right? And for the sake of brevity, I'm just going to leave it like that and say this is going to 0. So it's really just the natural log of Kr minus K over Kd. So if we put those numbers in, we should get a critical time of 2.31 days. That's going to mean that we can multiply this by the 60 miles per day that are traveled by the river, which gives us a distance of 138.6 miles downstream. Now, this is untreated waste from a food processing plant, and they've made sure that they're not discharging anything below the deficit of their for oxygen deficit, right? So they have no oxygen deficit. So if they're trying to be sneaky by oxygenating their waste stream before discharging, then their actual the worst case of their oxygen sag curve happens nearly 150 miles downstream. You might be able to see how you could potentially get away with that, right? So that's kind of an interesting thought here. Okay, so part C says what ultimate BOD, so L naught, milligrams per liter of the mixture of river water and waste just downstream of the discharge point would cause the minimum DO to be 5 milligrams per liter. Okay, so now that we've identified the time, we're going to go back and say, okay, well, what is the what is that actual L naught that's involved here? So L naught is the question when the deficit is equal to 5 milligrams per liter. Okay, so we can use our equation again, and this is going to be our D equals the KD L naught divided by KR minus KD. Now we have that other equation for use when the KR is equal to KD, but that is not the case here. So we have times e to the minus KDT minus e to the negative KRT plus the D naught that goes to 0. Okay, so using that, we actually have all of the values here now, except that we know D is 5, and we're solving for L naught. Okay, so it's just a bit of algebra from here. And we should get a value of 31.75 milligrams per liter. Now, if you had used the other equation for D here, you could have found an answer. So the one that's for when KR equals KD. So you're not supposed to use this one in this condition, but you could have used it. If you did, your answer would be about 17 milligrams per liter or thereabouts. So you can check your own work if that was something you did. That's why you would have gotten the wrong answer. Okay, last it says sketch the DO curve here. We kind of already did this, but basically we have some saturation value, and I think that was 10 milligrams per liter. We have the 3 and the 5 points here, and so initially it looked something like this, where that would be our was it 2.6 days? I forget what the number was. 2.31 days. So this x-axis would be time or distance, or it would be 138.6 miles. And then after the change, looks pretty similar, where we have a minimum point. Same time, same distance, just a different spot. Okay, and to answer the second part of part A, would a primary treatment plant be sufficient to achieve the reduction? So if you only have to reduce it by 28%, there's a pretty good chance that a primary treatment, just some sedimentation, usually removes a decent amount of stuff because there's some solids that can settle typically. So actually, yes, that would probably be a pretty cheap and effective solution for their situation. All right, any questions you want to talk about? Oh, last thing I did want to say, please remember to fill out the course evaluations. They are completely anonymous, so you're welcome to provide any sort of feedback you want. I'll happily read it. I'd be especially happy if it's constructive. Feel free to be critical or whatever, but love to hear what you think. And it's also good just for the college in general to see how everybody's doing. So please do that. Okay, so good luck on your exams. See you next week. Yeah, exam will be in here.